So far, we've taken a look at the bonding in various materials. In ice, the covalent bonds that exist inside the water molecule and the intermolecular bonds between the water molecules. In ionic materials such as table salt, we've studied the ionic bond. Now I want to look at the bonding that's present in metals. First off, a definition of a metallic bond. It's the electrostatic attraction between a lattice of cations, or positive ions, and delocalized, or free-to-move electrons. Consider, if you will, a potassium atom. It will tend to lose that 1,4s electron and develop a positive 1 charge. Here I've represented it by this diagram. If we arrange these now in a lattice or an orderly pattern, this is perhaps what the metal would look like. We have the cations in a regular pattern and the electrons buzzing around, free to move. And here, the electrostatic attraction, the attraction between opposite charges. The strength of that bond can depend on a few factors. How many valence electrons there are that are cast off and become delocalized, the charge of the cation, and finally the radius of our cation. Let's take a look at the effect of charge and the number of valence electrons. Calcium has a 4s2 configuration. That means it has 2 valence electrons it could potentially lose. As a result, its cations would have a positive 2 charge. So its lattice would look something like this. Our electrostatic attraction in this case would be much stronger, both because we have more electrons and we have a greater charge on our cation. In fact, that's reflected by looking at their melting points. Calcium melts at 842 degrees Celsius and potassium at around 64 degrees Celsius. Let's look a little bit more at potassium's family in the periodic table. As we move to smaller atoms like lithium, we can see that the electrostatic attraction is increasing, indicated by the higher melting point at 180 degrees Celsius. Let's look at some of the properties of these metallic bonds. Metallic substances are the first substances we've come across that are actually good conductors when they're solid. And that is because those electrons are free to move. They're not bonded or tied to any one particular cation. So if we place it between charged plates and throw the switch, we can get a flow or movement of electrons. Those electrons aren't held in pace and can therefore respond as other electrons move nearby. They can be repelled and move. The bond is also what we call non-directional. It exists in all directions. This allows our metals to be malleable or bendable, or they can also be drawn into a wire. Again, consider our lattice arrangement. If we apply pressure to a particular atom or group of atoms, we're not going to break the metallic bond because the metallic bond exists in all directions, and this will allow our cations to easily slide over each other and thereby not disrupt the bond. We can make it a little bit harder for our atoms to slide if we introduced other elements, and these form what we call our alloys. For instance, the introduction of carbon atoms to iron atoms would produce steel, a much harder substance than just iron by itself. So that's our final look at bonding. The next program we're going to take a look at a bit of a summary as we move across the group 3, period 3 elements and study the different types of bonds that are present. Questions are always welcome. Thanks for watching.